All right, welcome back. Thanks for submitting all the homework. Shamek has been grading them, so you will get the homework back soon. So we talked about projection radiography and computers in medical imaging, where we calculated CT image size and stuff. And then we learned about CT, and today we are doing something interesting, PET and ultrasound. All right, here we go. Let's number 4, PET and ultrasound. So in general, nuclear medicine imaging is quite different from general X-ray based radiology imaging. Okay, so it is based emission imaging. Okay, and emission imaging can be reconstructed into three-dimensional. So you can call it emission computed tomography. So by labeling a compound, chemical compound, okay, which possesses specific biological activity with a radionuclide tracer, okay, we can follow through that tracer through the body, okay, and then we can actually monitor and we can observe your body's metabolic process of that chemical compound with the nuclear tracer. Okay, so the neat thing about this nuclear medicine imaging is you can capture moment-to-moment changes of the concentration of the nuclei tracer. Okay, so it is not just a simple shot. You can actually acquire time-dependent change of that tracer. Okay, how your body can actually process that tracer. Okay, so it provides biochemical and physiological functions of your body in vivo. There are many different kinds of radiopharmaceuticals, but I want you to remember this one radiopharmaceutical. This is FDG. It is actually tagged with radionuclide fluoride, fluoro-18, FDG. So it works. Your body understands it as a glucose, and then your body will process FDG as a glucose. So you heard about PET-CT, right? So PET and CT were two separate imaging modality until someone figured out, okay, let's combine those two. Okay, so usually there's a ring for the PET, and there is another bore for gantry bore for CT. Okay, so here you see the sagittal image of the female patient of CT, then PET imaging of the same patient. So when you combine those by fusing those, you can acquire the images something like this. Okay, the same patient in coronal view. So you can see that CT provides very detailed, accurate anatomy, but it doesn't provide any distinguishable difference between tumor and normal tissue in terms of grayscale, whereas in PET, because the radionuclide, the glucose in this case, is consumed by the tumor more actively, so it shows higher concentration of FDG, so you can actually change the color scale. You can actually convert this grayscale image by assigning some color scheme. You can actually visualize your tumor's metabolic activity very clearly. So PET-CT can be used for different applications, to identify various types of tumor, okay, such as lung tumor, breast tumor, head and neck tumor. So it is used as to diagnose, where the tumor is, and then staging, how it is spread, if it is local or if it is metastasized, and also it's very commonly PET-CT is used for the follow-up. Okay, so follow-up after chemotherapy or surgical resection or even radiation therapy. Okay, so CT or MRI have a complicating appearance, because of this change of chemo or surgery. However, PET will provide this high concentration wherever the tumor is. So it's very, very unique information that PET can only provide. As I mentioned briefly, PET imaging itself does not have very high resolution. Okay, it doesn't have accurate anatomical information. I'll talk about there's reason why PET image resolution is that poor inherently. I'll explain it in next slides. But by co-registering, rather fusing those PET image with the CT, with the same position, so it's acquired actually at the same time, about close time together, you can acquire detailed patient anatomy. And then PET imaging, which is metabolic activity of the tumor, can be displayed on top of very accurate CT image of the patient. Since FDG is the most common radiopharmaceuticals in PET imaging, let's talk a little bit more about FDG. So FDG, which is actually tagged with this F18, which is actually radioactive material, it is, like I mentioned, this glucose analog. That means your body thinks it is just regular glucose, okay? And it is taken up by any cells that use high glucose, such as brain, your kidney, and of course cancer cells. Okay, the uptake, the term uptake means it is actually, it absorbs, it uses more, right? The uptake rate is proportional to the cell's metabolic activity. Okay, so I'm not going to go detailed because I don't claim myself actually expert in this mechanism, but you can simply understand this. The FDG goes into the patient, patient cells, and then it gets trapped, okay, inside the cell, not like any other glucose. This FDG glucose gets trapped inside the cell, and then it is actually emitting this positron that I will explain later, and then we detect that annihilation photon from that positron and negation. So how do we make this FDG18? So FDG in this F18 is produced in cyclotron, okay, by bombarding this oxygen 18 water with proton. Okay, so this is oxygen 18 water, then you bombard with a proton, and then you end up getting this F18. Okay, so F18 and oxygen 18 are isobars. What are isobars? Isobars is the same atomic number with different Z. F18 is unstable radioisotope, and then it wants to decay. Okay, it wants to decay, and then it becomes more stable oxygen 18. Okay, by emitting this is key. Okay, this positron. Okay, this is positron, and then neutrino. Okay, and the half-life of that processed radioactive decay is about 2 hours. Okay, so it's rather short. Okay, but the key thing is from here to there, it emits this positron. Okay, so this is actually F18. Then it emits this positron. Okay, positron, it cannot travel further. Okay, it almost immediately interacts with electron. Okay, electrons are everywhere, and then it emits this 2 gamma ray. Okay, 2 X-ray. Okay, at opposite direction. Okay, near. Okay, this key is near. It's 100 degrees apart. Okay, and the energy of that each photon is 511 keV. So that is why, because that is actually the mass energy of the electron, right? So then those 2 photons traveling to opposite direction will be detected by using this unique mechanism of coincident detector system. Okay, so we have to detect this. Okay, so if you think about it, that 511 keV is rather high energy. Okay, so that you need a detector system with a high Z material. Okay, so usually people use scintillating material here, scintillating crystals, coupled with photomultiplier tube. Okay, so in PET scanner, you have this ring of detectors, okay, around the gantry. Okay, so the common detectors in PET scanner has to have a high density and high Z. Okay, so you can use BGO, LSO, GSO, but it's okay. You don't have to remember this. But just remember that it uses scintillator coupled with photomultiplier tube, and you have to have some high density, high Z material. So we now have to detect. Okay, so say there's a one event of annihilation, then the photon will travel to opposite direction, right? But there is going to be millions of billions of interaction like this. So how do we know that where that signal is coming from? Okay, so we're going to introduce this concept of coincidence detection. So this is very, very important concept, coincidence detection. Okay. All right. So what is that? So there's actually, when the signal is coming from here, okay, you have almost 180-degree apart signal. So there's detector this guy and detector this guy will detect the signal almost at the same time. Okay, so almost, when I say almost, well, the traveling distance is different, right, depending on where it is originated, but it's the speed of light, so almost identical. So channel 1, this detector will get signal all the time, right? And then channel 2 will get signal from all the time because there are tons of other signals. But when they both, channel 1 and channel, when they both receive the signal at the same time, you can say that, okay, along this path, there was one event. Okay, so that event can be tricky. The detection can be tricky. So in example, this ideal situation is this type of event where there's event and then two photons coming opposite, travel opposite direction, then you get true coincidence. Okay, but you can easily imagine that if there's a two event, okay, happened, then it emits two photons in both direction, and then this event emits photon direction, and this detector and this detector can have event coincidentally. Okay, so but this is random coincidence, not true coincidence, because there was nothing happened along this path. Right? So this is error. This will actually contribute to the noise. And there is another example where the event, the photon, traveled at first to opposite direction, but it is scattered. Okay, then it traveled to there. So the detector system will consider this as a coincidence and then assumed that the event has happened along this path, but in reality it was just a scattered coincidence. This coincidence detection system is very inefficient. That's actually one of the reasons why PET image is actually such a noisy, low resolution. So first reason, not only 15% of the photon escapes patient body, the coincidence circuit has to discard 99% of the detection, as they are considered single event, because you can imagine there's only 1% of chance that two photons that is traveling opposite direction is detected by this system. So let's talk about attenuation correction. So PET scan, the radiation source is inside of the body, right? So the signal, the X-ray strength, when it came out of the patient, will depend on how much of the body actually it passed through, right? So if it is from the lung, or if it is from the skull or brain, the amount of attenuation needs to be taken into account. So PET scan needs this attenuation correction map. Okay, so there are different ways of creating this attenuation correction map. So one way is the germanium-68 radioisotope source. the patient is inside the bore, and then this radioisotope source rotate around the patient and sort of like creating tomographic image. Okay, so they do that with the transmission one, and then with patient and without patient, and then it creates attenuation correction map. Okay, so PET scanner usually you can have just without correction, without AC stands for attenuation correction. There's nothing in the lung or you don't see anything, but with appropriate attenuation correction, you can say that okay, signal from inside the lung is actually, there's less tissue of the lung, so you have to give more weight, right? So I mean, it's rather the other way. You have to give less weight, right? So okay, now the signal strength that is coming from the lung will be corrected for its attenuation. Okay, I hope it makes sense. So the way that it creates this attenuation correction map is traditionally for PET was using this germanium 68 isotope. However, because now we have PET CT, the CT image itself can be used as a very high resolution attenuation correction map. Okay, so here's a two comparison between germanium 68 based attenuation correction versus CT. So one thing nice about this germanium base is the energy of this germanium 68 source is the same as the positron annihilation photon from the positron electron annihilation. So that is actually very accurate in terms of attenuation, because it's the same energy. However, the X-ray, the CT scanner X-ray is, as you all know, is like about 100 kilovoltage peak, so which is significantly lower. So attenuation might not be very accurate. However, it is much less noise and image quality is much better. And then it also takes significantly less amount of time to generate this attenuation correction map. So that's why in PET CT, CT itself is used for the attenuation correction. So this is typical PET CT image acquisition procedure. Before the scan, the patients are asked for typically 4 to 6 hours of fasting to enhance this glucose uptake. Okay, and typical dose of FDG is 10 millicurie, and it is injected via intravenously. And the patient activity and speech has to be limited, okay, to minimize muscle uptake. Okay, and then PET is performed and then followed by CT scan with the same patient position. Okay, so as you all know, CT only takes less than a minute to scan. However, PET scan usually takes 30 minutes, or as long as 45 minutes. So let me conclude PET CT lecture with this slide. Let's talk about image artifact. What kind of image artifact can happen in PET CT? So as I mentioned just now, because PET CT utilize CT image to correct attenuation, any artifact from CT itself can play some role in PET image reconstruction. So if CT has a breathing motion artifact or metal artifact, etc., it will affect PET imaging. And also, next concept is very important to understand. So it's called positron range blurring. Okay, so if you remember what I said earlier, this positron that's coming out of this FDG has to travel, even though it is very short distance, it travels before it meets electron and annihilate. Okay, that inherent distance can cause some discrepancy between where the FDG isotope is versus where the signal originates. Okay, so the CT scanner, the PET scanner will say, okay, the event is happened actually at this point, whereas in reality, the FDG is positioned on your left. So there is this blurring, or like degradation of the image quality. The other the other artifact is annihilation angle blurring. Okay, these two annihilation photons are not exactly 180 apart. Okay, so there's a slight degree of uncertainty. We don't know. It's sort of random, and then that causes, like very low efficiency of coincident detection. So, these three artifacts, it's actually, I think it's important to remember. So what kind of PET imaging artifact can happen? CT attenuation correction artifact itself, and range blurring, and then angle blurring. Okay, let's move on to our next topic, ultrasound imaging. So ultrasound imaging has nothing to do with X-ray. Okay, it is actually a mechanical way of acquiring image using sound. However, we have some use in our department or in our field, so I believe it's worth learning about ultrasound. Okay, all right. So ultrasound, as the name implies, is high frequency sound wave. Okay, so you cannot really hear it because it exceeds our hearing range. Ultrasound utilizes energy and acoustic properties. Okay, we'll talk about acoustic properties later. So acoustic properties of body to produce image. Okay, from the stationary or moving tissue. Okay, stationary, like you can see the liver, thyroid, or like a moving tissue, or like a blood, okay, moving through your heart. Okay, you can actually detect, or like fetus inside the mom is actually uterus. Okay, so it's also known as pulse echo imaging. So it is a mechanical interaction of short pulses, okay, bunch of pulses sending out from the transducer, and then the echo will be detected by the transducer itself, okay. So it is this time between the pulse and the amplitude of the echo that makes this ultrasound image, okay. So how fast or how late the sound that is sent out from the transducer comes back, okay, how fast it comes back or how late it comes back, and then how strong it comes back, okay, that tells what's behind the boundary. So that's how ultrasound images are created. All right, to understand ultrasound, we need to define some physics term, okay. So maybe some of you guys are already familiar with this term. So let's define wavelength, and then frequency, and then speed of the sound, okay? So wavelength is from when you have this, sinusoidal wave, the wavelength is from start with the one cycle, right? So either peak to peak, valley to valley, or when wave crosses zero to end in this full shape, okay? So that's wavelength, okay? How long it is, okay? So wavelength is by definition is a unit of length. And the frequency, what is frequency? Frequency is the number of times the wave oscillates. Okay, how many times it goes up and down, okay, through a full cycle per second. Okay, so the hertz, okay, 1 hertz is by definition 1 cycle per second. So that means, from like this to this, it takes 1 second, okay, time-wise, okay, 1 second. That means it is 1 hertz, okay. So medical ultrasound has frequency of typically 2 to 10 megahertz. That means for 1 second, you have 2 to 10 million cycles, okay. All right, so let's also define the period, okay. Period is the time duration of the one wave cycle. So it is by definition inverse of the frequency, okay. All right, so what is the speed of sound then? Okay, speed of sound is wavelength times frequency, okay. So again, wavelength times frequency. So in soft tissue, the speed travels at different speed than inside the fat, okay. So of course the sound will travel different speed in the air. So what do we mean by higher frequency or low frequency? Okay, so here your x-axis is distance. Okay, then your y-axis, you have three different frequency ultrasound. The first one is 2 megahertz, sort of like a low frequency, and then 10 megahertz. So the one cycle, okay, one wavelength is a lot longer for 2 megahertz compared to 10 megahertz. So 10 megahertz, higher frequency, has shorter wavelength, okay? And that typically creates high resolution image, okay? However, the depth of this sound beam penetration is significantly reduced for the high frequency ultrasound, okay? So for like thick body, to visualize, say, liver or fetus, like abdominal imaging, you want to use lower energy so that it can penetrate deep, right? However, some shallow organs such as like thyroid or breast, you want to use high resolution, high frequency ultrasound, because that will give you higher resolution image. So in short, deeper sound, like a lower sound, travels further than high pitch. So we want to define this material specific property, okay, of acoustic impedance, okay, Z. So it is a fundamental property of the matter, okay. So let's define Z as this, okay, rho times C, okay. So acoustic impedance is defined as density of that matter, that material, times velocity of sound. So again, it's Z equals density times speed, velocity of sound. So density has, what is this, a unit for density? So kilogram per volume, right? Cube times meter per second. So that gives this interesting unit for acoustic impedance. Okay, so we'll cancel out, you'll have this, and then second. So you want to notice that air has very, very, very low acoustic impedance, okay, compared to high density material. Okay, so low density, you can kind of imagine, okay, the density plays big role in acoustic impedance. Okay, so air has very low acoustic impedance, and then high dense material, okay, will have higher acoustic impedance. All right, so why did we define that? This sounds like complicated term of acoustic impedance, because we want to actually quantify how much of the sound will be reflected, okay, or refracted. So okay, let me explain this. So the sound, say, imagine sound is coming from the top, okay, and down, and there are two different material, okay, material Z1, okay, material 1 and material 2, which has different acoustic impedance, okay. Z1, the material up here, let me use this pen, material up here has density of rho 1, then velocity of sound of C1, okay. Whereas down there, you have another material like this. So the amount of reflection that goes back, okay, you see this dark arrow here, that has to do with the relation between Z1 and Z2, okay. And then also it is acoustic impedance, that the amount of refraction, okay, it basically determines the amount of refraction depending on the incident angle. So this material difference is very, very important. So this equation right here determines how much of the sound will be reflected back. Okay, so imagine you have a muscle and air interface. Okay, so you have sound coming down from the top. Okay, so you have muscle. Okay, muscle, and then say you have air. Okay, so what did I say? Air. Say like it is. What is acoustic impedance of air? Okay, what is acoustic impedance of muscle? Okay, you don't have to remember, but I told you that it is significantly smaller, right, for the air. So say 0.0001. Okay, then the muscle, let's say it is 1.5. Okay, I mean I'm neglecting this unit of 10 to the 6. So say imagine Z1 is about 1.5, Z2 is 0.0001. Then what is our R? Okay, R is, okay, here you have 0.0001 minus 1.5. Then you have 0.0001 plus 1.5, okay, to the square. So you can, I mean, you don't have to run the calculator, but you can say this will be close to, very close to 1, but just slightly smaller than 1, okay? So say 0.99. Okay, what does that mean? What does that mean is when you have sound, okay, coming through the muscle, and then when you have air, okay, you will have significant reflection. Okay, the huge amount of sound wave will reflect it back. Okay, that means it basically renders, you cannot see anything beyond this air. Say you have another layer behind this air that you want to monitor. Okay, say you have prostate, for example. Okay, if you have this air in the middle, you cannot observe any signal. Does that make sense? Okay, hopefully it makes sense. So the air is enemy of ultrasound. If you have air pocket, you cannot see behind air. That's why. The sound wave does not always incident upon the boundary like this, right? So most of times, if there is a boundary of, say, muscle, bone, muscle, fat, the times depending on how you orient it, the sound wave we can bounce off or it can refract. So there is this physics, Snell's law, that can help us to quantify how much will be reflected, refracted. Okay, I mean, I don't expect you to guys actually remember this, but just remember there's reflection and refraction going on when you when you send this sound through the probe of the ultrasound. Okay, so the ultrasound probe, okay, what's it made out of? It's special material called piezoelectric. Okay, so this piezoelectric material is the functional component of this ultrasound transducer in this picture. Okay, so what it does is it can convert electric energy into mechanical energy. Okay, so this sound is nothing but the mechanical vibration. Okay, so by applying some electricity, you can control how much or how fast or the frequency sound comes out of this material. Okay, so I have a next slide to explain it graphically. But at equilibrium, there's no charge, okay, at the surface. But when it is compressed, it has imbalance the surface of this crystal that can actually create charge on the surface. Okay, so well, in ultrasound, actually, it uses synthetic material called PZT. Okay, so let's talk about these 3 bullet items with the graph, with the figures in the next slides. All right, so on your left, so in the at equilibrium, there is no surface charge. Okay, the molecules or like atoms are randomly distributed, so there's no net charge at the surface. But when it is compressed, okay, it can create this positively charged to the one surface, and then negatively charged on the other surface. And opposite, and when it is expanded, it can be aligned. The charges on the surface is realigned, okay, and then it now has opposite charge on this, okay. So in other words, this compression or expansion can change the charge on the surface. So you can utilize this in the opposite direction, okay. Instead of physically compress or expand, this time you are applying this charge, okay. So by applying this charge, positively charged charge or negatively charged to one side, you can make this piezoelectric material to compress or expand, okay. So by controlling the surface charge, you can make this piezoelectric material to expand and compress really fast, okay. So basically vibrate, it can vibrate. What happens if you make it ultra fast vibration? That it creates sound wave. All right, there are different types of transducers available. So here I'm showing the linear array and then sort of a curvilinear array. And next slide, I'm going to talk about the phased array. Okay, so linear array and curvilinear arrays are very similar. Okay, the only difference is it's more like a straight image it will create, whereas in this view you will have this trapezoidal, like a fan-shaped image it will create. So the ultrasound sound will sweep across. Okay, then ultrasound will sweep across like this shape. So as it goes, send the signal out, it also detects. Okay, send signal out, then it detects the echo, send signal out and echo. Okay, so it's array. The phased array, however, is different. Okay, it has a lot smaller. The transducers are a lot smaller, but you can actually control where to send the sound. Okay, so by steering, this beam steering called. Okay, so even though it is small, it can sweep through a larger area. Okay, so it's a lot more advanced way because the probe doesn't have to be large. So here is the example of curvilinear array. It has its curved surface. Then this is a lot smaller. It is actually phased array, so you can sweep the sound across. This is somewhat special. Okay, this is what we call intracavitary ultrasound probe that we are using this in the prostate implant. For example, you'd place this inside the patient rectum and then point it toward the patient prostate, and you can see it. So you can place this in intracavitary. In ultrasound, there are 3 different kinds of image acquisition mode. So A stands for the amplitude mode, and B is brightness mode, and M is motion mode. So A mode, it will create image something like this. Okay, it's not even image. Okay, it is more like a plot. Okay, so say this is ultrasound probe up against the patient body. Okay, so you have a fat, you have muscle, fluid, and another muscle and bone. Okay, the A mode will create this sort of like a plot. Okay, sort of like what do you call it? Peak. Okay, whenever it sees boundary. So there's a fat and muscle boundary, it'll create the peak. Then muscle and fluid, it'll create a peak. Then muscle and bone, it'll create difference. So the peak, the height of peak can tell you, the material difference between those two, across the boundary. So that's A mode. So again, the A mode displays the interface, okay, and it plots as an amplitude, like here, like this. Okay, so there's no 2D image. So what you see here, this is not A mode. This is A mode. You see it's a plot. Okay, so for example, okay, eye doctors use this A mode. So this is actually the A mode and B mode combined together. But look at only this plot. So the probe is on the patient eye. Then you have this eye, and then you have fluid, and then you have tumor. Then it shows peak, then it goes down, and then normal tissue. So by measuring this amplitude, okay, you can kind of tell, okay, there's some abnormality there. And then you can also sort of measure the peak width to estimate the tumor height. Okay, here's another example. What you see, this is A mode. Then you have these peaks of the normal tissue, you have lens, cornea, and then you have tumor. So you can tell that, okay, by measuring from here to there, you can estimate the tumor height. Okay, next, B mode. B mode is actually most common ultrasound mode. Okay, so it basically converts that, instead of showing the peak plot, which is not very intuitive to our human mind, it basically converts the peak signal into a different grayscale. Okay, so in B mode, you see the grayscale image. So if you have like a baby, you send a sound signal, and it basically reconstructs the echo. Then you see this very nice two-dimensional black and white image of what's inside the patient body. So this M mode, motion mode, is very similar to B mode. Okay, so it uses this grayscale image to display the echo of, usually, it uses, as the name implies, moving organs, okay, such as heart imaging, okay, the valve leaflets. So you fix the transducer position of and beam direction, and then you acquire image over time. Okay, so it's a great way to acquire temporal change of the patient, especially heart. Okay, I'm not an expert, but you basically fix the transducer location and direction, and then you monitor the change of the image along this sort of like array. Okay, and then on your x-axis will be your time. Then these lines of images shows B mode sound image. Okay, so you can kind of tell. I mean, I cannot, but expert can tell there's abnormality in the valve open and close and that sort of things. Okay. So the ultrasound image, I mean, it's not that popular, but you can use this in-room ultrasound image to basically localize prostate, for example. Okay, so this special ultrasound probe has this optical tracking markers. Okay, and then therapist would position patient, then look at the ultrasound image of, say, prostate, for example. Okay, and then the ceiling mounted optical camera can see these optical reflectors and then can register patient position to the planned location. Okay, so say any given day, if patient prostate is left to right, sub-inf different, then the computer can calculate based on the real-time image of the given day. It can calculate the shift. Okay, but it's not that popular. All right, another great application of ultrasound in our field is brachytherapy of the prostate. Okay, so you have this transrectal ultrasound probe that is inside the patient. Then the ultrasound can come anteriorly to visualize patient prostate in real time. Not only the prostate, but also it can visualize the needle. Okay, so how deep it is. So you don't want to puncture the bladder, for example. And then, so in this example on your left, I'm not sure how well you can see it. It is actually brachytherapy planning of the LDR seed implant in prostate. Okay, so using this template, we can actually design the plan where to place seed and where we want to not place a seed in urethra, for example. You can cool off, and then you can create this very uniform those around the prostate. All right, that's all I have for now. Later this week, I will upload another lecture about MRI. And then next week, we will wrap things up. Just briefly talk about in-room imaging, like cone beam CT and OBI stuff. And all right, thank you very much, guys. See you next time.